right? So if you remember last class, what we were doing was we had a sequence of we had a sequence of independent Bernoulli random variables. Okay, and when you have a sequence of independent Bernoulli random variables, here each xi is either uh, 0 or 1, and we interpret 1 as success and 0 as failure. Okay, and let's assume that these are all they're all Bernoulli P random variables. Okay, the question we asked last class was, what is the time till the first success? Okay, right. So T is the number of trials till the first success. Okay, so we were trying to see how T would look like, and what all values T can take, and what are the probabilities of each of these values. So this is how far we came. We said first of all that okay, so the probability T equals 1. T equals 1, the event T equals 1, right? So this is the event x1 equals 1. Okay, when we say x1 equals 1, one point to note is that we are not saying that we won't do the remaining trials. Okay, it's more cleaner to think of it this way. When we write x1 equals 1, okay, what it means is that x1 equals 1, x2 can be anything, x3 can be anything, and so on, right? So that's what we really mean when we write x1 equals 1. Okay, it does not mean oh sorry. Okay, sorry, like I think maybe I cut out a little bit there. So when we say x1 equals 1, okay, what we really mean is that x1 equals 1, x2 can be anything, x3 can be anything, and so on. So the values for x2, x3, x4, they're all, we don't care, okay, or it includes every possible value for x2, x3, x4, so on, right? So so this is what we mean by saying x1 equals 1. Okay, it's a very helpful nuance to think about what happens in other what happens. Okay, so for example, when you want the event x2, sorry, t equals 2. Okay, here we do know x2 has to be equal to 1 here, but that is not enough. Okay, because we cannot ignore the value of x1, right? So in this case, this has to be x2 has to be 1 true, okay, but we are not able to ignore the value of x1. X1 must be 0, right? Because if x1 was 1, t would not be 2, t would be 1. Okay, if x1 equals 1, your first trial was already a success, so the time to the first trial was 1. Okay, so here for the event t equals 2, when we write out this event, we cannot ignore what happened to x1. Okay, we must have failed in the first attempt to have succeeded in the second attempt for the first time. Okay, and same thing, like probability t equals n. So what is the event t equals n? What is the event that t equals n? Right. So it is not xn equals 1. Okay. Because for t equals n, it is the number of trials till the first success. Okay. So if you do not know what happened before, just the fact that knowing t equal xn equals 1 does not imply that t equals n. Okay. Xn has to be 1, of course, but also x1 through xn minus 1 must be equal to 0. Okay, if any of the prior bits, right, so if any of the prior bits were 1, okay, t would be less than n. Okay, so now can you tell me, it's slightly more complicated event, what is the event that t is greater than or equal to k? Right, so I know that this is the event that t is some value greater than or equal to k. Okay, it could be equal to k, it could be equal to k plus 1, k plus 2, any of these, but some value greater than or equal to k. Okay, what is this? How do we succinctly write this event?
Everything below 10 is 0.
Right, so we must have x1 through xk minus 1 must be equal to 0. Right, as long as we have failed in the first k minus 1 attempts, okay, the time till the first success is greater than or equal to k. Okay, does that make sense? Okay, right, so we also wrote the probabilities of some of these events. Okay, so we wrote the universe, right? So the universe, we would say, is something like 1 0 1 0 0 1, where the sequence we interpret it as x1 equals 0, x2 equals 0, x3 equals 1. Okay, and so on. Right, so a string of zeros of any length, okay, and followed by a 1 at the end. So this is our universe. Okay, and this universe is not finite, right? So there's no, the number of elements in this universe is no longer finite. Okay, that corresponds to t taking any positive whole number as a value. Okay, t can take 1 2 3 4, any positive number as a value. Okay, uh, so but what is the probability t equals 1? This is the probability of the event x1 equals 1, which is p. The probability t equals n is the probability of the event x1 equals 0, x2 equals 0, right? And we know these are independent Bernoulli p random variables. So what's the joint probability? X1 is 0, x2 is 0, and so on. So what is this probability?
Is it 1 minus p to the power of n minus 1 times p?
Right, right? Because they are independent, this is the probability that t equals n. Okay, and so this is the probabilities we assign to every outcome in the universe. Okay, the probability of the universe has to be equal to 1. Okay, and sure enough, like this is p plus 1 minus p times p plus 1 minus p squared times p plus so on. right? So this is the geometric sum 1 minus p to the n times p, where n goes from 0 to infinity. How do you do this sum? Right, so this sum is indeed 1, has to be, okay? So the probability of the universe has to be 1, and this sum will be indeed 1. But just in case, any uh, for any x strictly less than 1, what is the sum of 1 plus x squared all the way to infinity? Tell me, what is this? The sum of the first n plus 1 terms in the geometric series? Let's write first. Okay, so let's write the sum of the first n terms of the geometric series. Okay, not n plus 1. It's this one will lead to easier symbols. Okay, what is the sum of the first n terms in the geometric series? How do you do this? Right, so how can we do this summation? So no one has seen this before?
It's been a while.
But the procedure is actually almost unforgettable. Like the answer may be difficult to remember, but the procedure is not. So, okay, so here is what you do: multiply Sn by x. If you multiply Sn by x, what do you get?
X plus x squared plus x
Right,
cubed all the way
x
up to
plus
xn.
x squared all the way through xn minus 1 plus xn. Right, if you multiply by x, this is what you get. Okay, for the n terms, just get shifted by 1. Subtract these two together. So what do I get on the left side when I subtract x times Sn from Sn? Right, so I get 1 minus x times Sn. On the right, what do I get?
1 minus x to the n.
Right, so when I subtract on the right, I only get 1 minus x to the n. Right, everything else cancels. Okay, so what is Sn?
1 minus x to the n over 1 minus x.
So 1 minus x to the n divided by 1 minus x. Okay, now x is less than 1, x is strictly less than 1. Okay, so what is the sum? What is S infinity? Right, so if x is a number less than 1, okay, like 1/2, right, what is so x squared is less than x, okay, x cubed is less than x squared, right? So x to the n keeps decreasing with n. Okay, what is the limit as n goes to infinity?
Would it be negative infinity?
No. So this is the limit as n goes to infinity of Sn. Right, so here this is basically 1 minus x to the n divided by 1 minus x. Okay, so you have 1/2 squared. What is 1/2 squared?
1/4.
Right, 1/2 to the right. So what is 1/2 to the 3?
1/8.
Okay, so what is the limit of 1/2 to the n as n goes to infinity?
0.
0. Right, so what is the limit of Sn as so what's the limit of xn as so this is true for any x less than 1. Okay, what's the limit of xn as n goes to infinity? It is 0. Right, so what is s infinity?
1 over
0.
1 minus x.
No, it's 1 minus 0 divided by 1 minus x, which is 1 over 1 minus x. Right, so this is the infinite geometric sum. Okay, so can you do this sum for me? So Caleb, you're muted. You're saying something, but you're muted.
I'm not nearly confident enough to say it out loud.
It's okay. So how does it?
If I had to take a guess, and it's not like a high confidence guess, it'd be like 1 divided by 1 minus p to the n times p.
Right. So this is a sum. No. So first, let's write it as a geometric sum. We want to write it as a sum like this. Okay. Or rather, like as a sum of infinite terms, but like this, like a geometric sum. How do I write it like a geometric sum?
You
Right.
just start at the beginning of n equals 0. So like 1 minus p to the 0 times p, and then 1 minus p to the 1 times p. Sum across those. Is that what you mean?
Right, but okay, so probably you mean it this way, like first you have to pull p out of the summation. Okay, now the summation, like the index of the summation is n. Okay, p does so the term with p does not contain an n, so you can pull that out of the summation. Okay, now this is a geometric sum. This is a geometric sum where x equals 1 minus p. Okay, so what is this sum?
It'd be like 1 divided by 1 minus p to the n.
No. No, here, this is an infinite geometric sum. Okay, it's an infinite geometric sum. Okay, but the ratio between terms is 1 minus p. Right, so this is not a sum of n terms. When we write something like this is 1 minus p to the 0 plus 1 minus p to the 1 plus 1 minus p squared all the way to so it has an infinite number of terms.
Oh, would it be the limit as n goes to infinity of 1 minus the sum of
Not 1 minus p. This s infinity is not 1 over x. It is 1 over 1 minus x. Okay. So this
I'm gonna
is
stop guessing.
1 minus. No. What is the ratio? The ratio is 1 minus p. Okay. So it's 1 minus 1 minus p. Right. So is that right? So okay. So formally, like here, the ratio is x. Okay. The ratio between two terms is x. Okay. And x is what comes here. Right, so if the ratio between terms is 1 minus p, 1 minus p is what should come here. Okay, so this is p times 1 minus 1 over p, which is equal to 1. Okay, and this is so long as p is not equal to 1. sorry, so long as p is not equal to 0. Right? So if p is 0, then you'll never have a success. Okay, the probability of success is 0, that is, you'll never ever see a success. Okay, but so long as the probability of success is not 0, okay, this is our universe is a legitimate setup. Okay, and eventually you're going to see so one of these events, t equals 1, t equals 2, t equals 3, one of them will happen. Okay, right? So keep in mind, once again, let me write it a little cleaner because I hadn't expected this would be unfamiliar. Let's do this a little cleaner because this. Okay, so once again, this is the sum from k equals 0 to infinity, 1 minus p to the k minus 1 times p. Okay, now this is, you pull p out of the summation, right? Now this summation, so k equals 1. Okay, so this summation is a geometric sum. This is 1 plus 1 minus p plus 1 minus p squared plus so on. Okay, now to do this summation, what we do is we multiply this by 1 minus p. Okay, and I get 1 minus p plus 1 minus p squared plus so on. Okay, and I subtract the two together. So 1 minus p times s infinity is 1. Everything else cancels. Okay, and therefore, right, and this is true if 1 minus p is strictly less than 1. Okay, this means that p is strictly greater than 0. Okay, so here, so this geometric sum is important. There is, so let's say we do a little more, we do something a little more complicated. Okay, so we have this term, right? So let's compute the expectation of t. Okay, so let's try to compute the expectation of t. How do we write the expectation of t? Right, but okay, so is this part clear? Why the sum of the geometric series is 1 over 1 minus the ratio? Okay, so let's look at, so if we want to go over this again, let me know. We can go over this again. It's kind of important, so better we are sure about it before we proceed.
I don't mean to hold anybody back, but I would
We
benefit from
can do
going
it
over.
again. Like if you want me to go over
Yeah.
it again, like we can do it. Okay, so So all of these things, like it's better if you tell me what to do. Okay, so right, so this is the summation we want to compute. Okay, is this step clear? Right, so this is something generally true. You look at the index of the summation, or what it is summed over, or what it's integrated over. Any term that contains the index has to remain within the sum. Any term that does not, you can pull it out. Okay, so here this term does matter. I mean, this term does depend on k. Okay, you could pull out, for example, you could think of it as 1 minus p to the k times p over 1 minus p, and pull out p over 1 minus p. That is okay too. Okay, but anything that does not depend on the summation, on the index, you can pull out of the summation. Okay, this is just the distributive law. Okay, now this summation, when you have a summation like this, okay, initially at least, it helps to write out the first few terms. Okay, so what are the first few terms of this summation? You said k equals 1. Okay, so k equals 1 is the first term of the summation. Okay, when k equals 1, what is this?
1.
1 minus p to the 1 minus 1, which is 1. Okay, when k equals 2, what is this?
1 minus p to the first.
And so on. Okay, so this infinite sum is exactly what we have here. Okay, these are called geometric sums. Okay, what is happening between them is that every term is 1 minus p times the prior term. Okay, this term is 1 minus p times 1. 1 minus p squared is 1 minus p times 1 minus p. 1 minus p to the k is 1 minus p times 1 minus p to the k minus 1. Okay, every term is 1 minus p times the prior term. Okay, and that is what we exploit to do the summation. Okay, how do we exploit that? We multiply, we call let s infinity be the sum of all these terms. Okay, and this sum will exist so long as 1 minus p is less than 1, strictly less than 1. Okay, now if this sum exists, okay, multiply s infinity is a number. I can definitely multiply it by 1 minus p. Okay, so I multiply s infinity by 1 minus p. Okay, but when I multiply it by 1 minus p, I look upon the sum in a slightly different way. 1 minus p multiplies every single one of these guys. Okay, so I'm just going to write it in a way that makes it visually easier for me to see what is happening. 1 is multiplied by 1 minus p. I'm just going to shift it to the right and write it. Okay, 1 minus p gets multiplied by 1 minus p, giving me a 1 minus p squared. Okay, I'm just shifting it to the right and writing it below 1 minus p squared of the original summation. Okay, so basically this term came here, this term came here, and so on when I multiply by 1 minus p. The reason I do it is that now when I subtract line 2 minus line 1, line 1 minus line 2. Okay, if I subtract line 1 minus line 2, all terms cancel except this one which does not have a companion here. Right? So what it means is that s infinity minus 1 minus p times s infinity is just 1. Okay, and that then I can solve for s infinity as 1 over p. Okay, this is how we do all geometric sums. Okay, so it's not important whether you remember the formula or something like that. That's not material. Okay, what is important is how to exploit the fact that there's a common ratio to do the sum. Okay, so is this clear? Okay, so let's go back to the expectation. Okay, so now this is a geometric random variable. So we say, okay, t, when we have, just to summarize, if x1 x2 are independent Bernoulli the random variables, t, which is the number of trials till the first success, okay, and here we are assuming that p is strictly bigger than 0. Okay, so when p is strictly bigger than 0, the number of trials till the first success is called the geometric random variable. Okay, now here we have probability p equals k. If you had the first success on the kth trial, okay, then it means you failed on the first k minus 1 and you succeeded on the kth trial. Okay, so this is the probability that t equals k. Okay, now what is the expectation of t? How do we write it?
You would sum across the sample space for the 1 minus p to the k minus 1 times p.
That is fine. That is good. So either we sum over every point in the universe, okay, every point in the sample space, the probability of that point times the value the random variable takes at that point. Okay, what's the other way to write the expectation?
Would be like the probability of x divided by the indicator of x.
No. The other way to write it is I sum over all values t can take. Okay, and I write okay. So what are all the values that t can take? What are the values t can take?
It would be like 0
T
through
can't be
k,
0.
right?
T can't be 0. The random variables are x1, x2, so on. So t has to be 1, 2, 3, so on. Okay. So the values t can take are 1, 2, 3, and so on. Okay. We call these natural numbers. So these are all the values t can take. Okay. Now I sum over every value that t can take. What do I sum over? Okay, let's start the index as k. The value times the probability t equals k. Okay, so this is they're both completely equivalent, and in this case you can do it either way. Okay, we'll do it this way. If I write it this way, this is summing over from k equals 1 to infinity 1 times what's the probability t equals k. I know it's there right above, but can somebody tell me what's the probability t equals k?
The 1 minus p to the k minus 1 power times p.
Okay, so this is the probability t equals k. Okay, now this is the summation k equals 1 to infinity k times 1 minus 1 Okay, so can somebody tell me how this summation looks like? Expand out, tell me the first few terms.
It'd be 1 times 1 minus p to the 0th times p, so it'd just be p.
Okay,
And then k is equal to 2 would be 2 times 1 minus p to the first times p.
k equals 1. Okay. 2 minus 1 is 1 times p.
And
times
k is equal to 2. Yeah.
and so on. Okay, so here, like this summation, so if I want to, if I want to see which terms depend on k, which terms do not depend on k. Now again, this p does not depend on k. Okay, so let me pull this out of the summation. Okay, the equivalent way to look at it is this. I pull this p out of the summation, I pull it out of the summation, so what remains is 1 minus p to the 0 plus 2 times 1 minus p to the 1. So, okay, how do we do this sum in the brackets? Okay, what do these terms look like to you?
Is that like the geometric sum again?
No, this is not the geometric sum. Like, so the geometric sum means that the ratio between consecutive terms should be the same. What is the ratio between the first two terms? Second term divided by the first term. It's 2 times 1 minus p. Okay, the third term divided by the second term. It's 3 over 2 times 1 minus p. Right? So this is not a geometric sum. Okay, so what we have is something like this. X to the 0 plus 2x plus 3x squared plus 4x cubed. What will be the next term?
5x to the 4th.
Right. What is the, if I have x to the k minus 1, what is the coefficient of that? Okay.
It'd be k.
Right. So this is what the summation is. Okay. How do we do this summation? What do each of these terms look like to you? Derivatives of, very good, x to the k. Okay, so I'm going to write the real geometric sum here. Okay, so the geometric sum in blue is the geometric sum in blue is 1 plus x squared plus x cubed plus x to the 4 plus x to the 5 plus the kth term is x to the k and so on. Okay, so this is the real geometric sum. Okay, here what seems to be happening is that every term is the derivative of one of the terms in the geometric sum. Okay, and lucky for us, this equality will hold. This is not always true that in an infinite sum, if you take the derivative of every term, it's like taking the derivative of the sum. Okay, but in this case, okay, the left side will also be the derivative of the sum, where I see the sum as a function of x. Okay, so here, so what is s infinity of x? This we know how to do. This is 1 over 1 minus x. Okay, what is the derivative? So if I see it as a function of x, the derivative with respect to x is
Would it be a natural log of the absolute value of 1 minus that?
that no. The derivative, not the integral. There's no negative sign because it cancels with the negative sign here. So it's 1 over 1 minus x squared. Okay. The derivative of 1 over 1 plus x is negative of 1 over 1 plus x squared. But since we have 1 over 1 minus x, this will be what the derivative is. Okay, so this means that this s infinity, so this sum, therefore this sum, 1 plus 2x plus 3x squared, okay, this is 1 over 1 minus x whole square. Okay, so in particular, going back to our expectation, the expectation of t was 1 plus 2 times 1 minus p plus 3 times 1 minus p squared. Right? So what is the expectation of t? Right, so you know this. Tell me what is this sum? Right, so you replace x with 1 minus p. Okay, and that's all that is happening. Right, so this is p over p squared, which is 1 over p. Okay, this is actually very interesting. Okay, because what it tells you is this: if you have a coin, okay, where the probability of showing up heads is 1/4. Okay, let's say you have a coin where the probability of showing up heads is 1/4. Okay, how many times should you flip the coin, okay, before you see a heads? Okay, and this tells you that on an average you have to flip it 4 times. Okay, intuitively it makes a lot of sense, right? So if you have an event with probability p, okay, on an average you have to wait 1 over p trials before you see the event. Okay, before you see the event for the first time. Okay, it does not mean that your first coin toss can be I mean, when we say something like this, okay, so the expected number of coin tosses, assuming they're all independent, just before we see heads, it's 1 over 4, which is 4. Okay, so smaller the probability, the larger the number of trials before you actually see the event happen. Okay, but these are all averages. Okay, when we do these independent coin tosses, okay, it is quite possible that your very first coin toss is a 1, is a heads. Okay, it's also possible that you need 100 trials before you hit a before you see a heads. Okay, you could get 99 tails and then a heads. Okay, you could get a trillion tails and then a heads. Okay, and all of those are possible. Okay, but the most the expected value, okay, so the expected number of trials before you see a heads is 4. Okay, but also here there is something a little more subtle. What is the most likely value for t? Right? So here the expected value, the expectation of t is 4. Okay, what's the most likely value for t? What's the probability t equals 1? 1/4 in this case. What's the probability t equals 2? Not 1/2. Not 1/2. It is 1 minus 1/4 times 1/4, which is 3/4 of 1/4. Okay, 3/4 of 1/4. This is the value probability t equals to. What's the probability t equals 3? Right, so 1 minus 1 over 4 squared times 1 over 4. This is 9 over 16th of, okay, and so on. But all these numbers are all less than 1/4, right? So what is the most likely value for t? Yeah, so t equals 1 is actually the most likely value. Okay, but the average, the expected value for t is 4. Okay, but the most likely value for t is actually 1. Okay, so there's no contradiction. There's no contradiction because the expectation is just an average. Okay, but you need to remember that the expected value for t is not always the most likely value for t. Okay, in binomial random variables, they happen to coincide. Okay, but in most random variables, they do not. Okay, in the geometric random variable, for example, they do not. Okay, so is this clear?
Could you explain what you mean by the most likely value for t?
So which value of t has the highest probability?
Okay.
Okay, what's the value for t that has the highest probability? And that is t equals 1. Okay, okay, so does that make sense? Okay, so we can wrap up here for today. So now we know a little bit about binomial, geometric random variables, and so on. So next class, we are going to do a lot of simulations, and you're going to tell me what happens, what should happen. Okay, and we'll test your intuition, or we'll try to fine tune our intuition on all of this. Okay, so we are going to have like a, I'm going to ask you like what is likely to happen, and you tell me what is likely to happen, and we'll see if it is really true. Okay, so okay, so we'll stop here, but you can continue asking me questions.